Okay, let's practice this again. How about the following? So here's a vector field we haven't seen, but the vector field f of x comma y equals y plus 3x squared sine of y, comma x plus x cubed cosine of y. This is conservative. Though we haven't checked this, you could, partial derivative of this with respect to y is equal to partial derivative of this with respect to x. So you could check. Leave it up to you if you'd like to do that. But let's find a potential function lowercase f, right, such that when you take the gradient of this, you get back the vector field that we were given. So because we have a conservative vector field, it had to have been the gradient of lowercase f. And so then whatever that lowercase f was, we know that differentiated with respect to x, we'd have to result in y plus 3x squared sine y. And taking that same f and differentiating with respect to y, we'd have to get x plus x cubed cosine of y. So now let's go ahead and integrate with respect to x. You don't even have to memorize this. It's just there's a little x down there that this was f partially differentiated with respect to x, so we're just undoing that. And so then f of x comma y should be of the form xy plus x cubed sine y plus a constant as far as x is concerned, so g of y. Then if you take this, we're going to now intentionally differentiate this with respect to y, only because we've got an f sub y over here that we'll set it equal to in just a moment. So taking this and differentiating with respect to y, we're going to get this is equal to x plus x cubed times cosine of y plus g prime of y, and we set that equal to x plus, from up here we set that equal to x plus x cubed cosine of y. Now looking at this equation, we can subtract things on both sides, and we're going to get that g prime of y is equal to 0, and so then when we integrate this, we'll have g of y is equal to just a constant c. Okay, this tells us that f of x comma y could be xy plus x cubed sine y plus, there's a g of y, which we're about to replace with c. So we could put a c here, and if we want a specific example of a potential function, we could have xy plus x cubed sine y plus 1, 2, 3. Let's do this again. Let's do this one more time. Let's practice actually on a three-dimensional vector field. So let's take a look at the following examples. So we've got question. The vector field f of x comma y comma z equals angle bracket e to the x cosine of y plus yz, comma xz minus e to the x sine of y, comma xy plus z, close angle bracket. This is conservative. And then find a potential function. Find a potential function. Find a potential function called lowercase f. Now, we actually have not described how to tell that a three-dimensional vector field is conservative. That is coming, so don't worry about it for now. We're just going to go with it. We're just going to believe the information that we've been given that this is conservative. Here's the thing. If we have that this vector field should be conservative, then this first circled thing should be the result of partial differentiating f with respect to x, right? So f sub x of xyz should be the first component, should be e to the x cosine of y plus yz. And then the middle component should be f sub y of x comma y comma z. This should be equal to xz minus e to the x sine of y. And then finally f sub z. We don't know what lowercase f is yet, but if it really exists, you take it differentiate with respect to z, and you ought to be getting xy plus z. So let's go ahead and take the first thing here, and we will anti-differentiate with respect to x. So we're integrating with respect to x, and we should have here, well, integrate e to the x cosine y, and you actually get e to the x cosine y. But then the next term, when you anti-differentiate, you're going to get x, y, z. Now we need a constant that does not, but it's constant in the sense of it doesn't have an x in it, but it can have y's and it can have z's. So g of y's comma z. Now, because we want to set that equal to this, we can't set it equal yet because this is f sub y. So let's compute f sub y based on this. And so f sub y, now differentiating with respect to y. So there's a lot of anti-differentiating with respect to a variable and then differentiating with respect to another variable. So f sub y here is going to be, well, differentiate, okay, e to the x is a constant. Cosine of y differentiates to negative sine of y. Okay, so negative e to the x sine of y plus xz plus, now we need the derivative of this thingy here. Okay, it can mention y's or z's, the derivative with respect to y. So g sub y of yz. Okay, now we're going to take what we just got here, set it equal to what we have here. So we'll have negative e to the x sine of y plus xz plus g sub y of y comma z is equal to xz minus e to the x sine of y. The point is we can subtract an xz on both sides. We can add an e to the x sine of y on both sides. And we're going to get from here that g sub y of yz is just equal to 0. Oh, that's good. If it were messier, you know, we could deal with it, but it's just extra work. Let's go ahead and integrate this with respect to y to get that g of yz is now a constant as far as y is concerned. So it can be a function that mentions z still. So let's call that h of z. Now let's go ahead and take this line, the way we wrote f, together with how we know g of yz looks, and now write an updated version of f of x yz. So this is e to the x cosine of y plus xyz plus, g of yz, we now know we thought it was a function of both y and z. We now know what we have here is going to just be a function of z. That won't always work out, but we just get nice and lucky here. Now we're going to take this, and we would like to eventually set something equal to xy plus z, but to do that, we need f sub z. So why don't we take what we have here, and then we're going to go ahead and differentiate with respect to z, and we'll have here f sub z of x comma y comma z is equal to, well, that differentiates to 0, this differentiates to xy, and then h of z differentiates to h prime of z. Then we can set this equal to, let's be actually a little careful with our notation here. So we'll take this and that. These are both two ways of writing f sub z, and we will set them equal. So we have xy plus h prime of z is equal to xy plus z. Subtract xy on both sides, and you have h prime of z is equal to z. So now we need to integrate with respect to z, and we'll have h of z is equal to z squared over 2 plus now truly a constant. We don't need to bring x's and y's back into this. That will make things messy. So then we can go back to right here to the way that we had last written what f looks like. And so f of x comma y comma z is equal to, copying from right here, and that actually is we have e to the x cosine of y plus xyz plus, and then h of z, well, we now know h of z could be written z squared over 2 plus c. Z squared over 2 plus c. Okay, so then, as far as providing an actual specific potential function, we could have little f equaling e to the x cosine of y plus xyz plus z squared over 2 plus, I picked the number c to be 1, 2, 3, 4.